Okay, good morning, everybody. So in the previous lecture, we were talking about dynamic memory allocation. And we left off at this part of the notebook. So a function that needs to or wants to return an array, it can't return an array with automatic storage duration, right? Such an array doesn't exist after the function returns, so you have to dynamically allocate an array. And then you return a pointer to the first element of the array. Right, so here's a function that returns a pointer to an int, right? So it's a pointer to the first element of a dynamically allocated array of int, and the caller passes in how long they want the array to be. Right, so inside the function, we simply dynamically allocate that array of int right there, and then you just return ARR, right? And now the caller gets back an array of length, whatever length they asked for. Right, so the main function here allocates or asks for an array of 10 ints, and that's what they get back from the function. There is another way to do this. So the other way to do this is that instead of the caller assigning their pointer to the result of the function, they can pass a pointer to the function, and the function can set their pointer for them. Right, and so here we've got the following function. More or less the exact same thing, except this time, instead of returning a pointer to the allocated array, or a pointer to the first element of the allocated array, what this function is going to do, it's going to write the value of the pointer into a variable passed by the caller. Right now, if remember in C, if a caller wants a function to write into one of their variables, they need to pass a pointer to that variable. Right. So here, the caller wants the function to write into a variable that is a pointer, right? Pointer to the first element of the array. So for this function to work properly, it needs a pointer to a pointer, which is what this thing is here. Right. So int star star ARR is the way you read this is right, is a pointer, right, to a to a pointer. Right. So ARR inside the function is a pointer to a pointer. Right. And you treat it just like any other pointer. Right. So here we're going to allocate our another bug, length times size of int. That. Okay, so here we're going to allocate our array of int. Right. So notice I've created a separate variable here. I'm not going to try to do this all in one shot, although you could. Right. I'm going to create my new pointer variable here called buff. Right. Allocate an array of length right, that can hold length ints. For demonstration purposes, I'm just going to write into that array. Right. And now I want to set the caller's pointer so that it's equal to buff. Right. So I dereference their pointer that they gave me. Right. Remember, they gave me a pointer to a pointer. Right? They didn't give me their pointer. Right. They gave me a pointer to their pointer. So I'm going to dereference their pointer. Right? That gives me their pointer object that I can now write the address of the newly allocated array into. Right. So it's exactly the same as before when we had an example like this. Right. So here's a function that here's bad add one. So it tries to add 1 to the value x that the caller passes in. Right? So the intent of this function is that the caller calls add 1, right, with their variable, and then the value 1 gets added to their variable, right? So their variable goes up by 1. That doesn't work in C, right? So bad add 1 doesn't work, right? What does it do? It gets a copy of the value. It gets the value of whatever variable the caller passes in, right? It doesn't get the variable itself. It adds 1 to the parameter x, right, and then returns, which doesn't change the caller's variable. Right. So here the caller has a variable y, right? They want to add 1 to y. You call that add 1, it doesn't work. So y is 3. After calling bad add 1, it's still 3, right? If the caller wants a function to change a variable owned by the caller, right, they need to write the function such that it takes in a pointer to their object. So it's all the exact same thing, right? Here, the caller wants the function to write into that object there. Right? The only way that the function can do that is if they get a pointer to that object. So here, when you call int array, you pass in the address of A in this case. Right? Then up here, when the function dereferences ARR, right, they get A. Oops, they get A, right? And so that line there is just like writing A equals buff. And so that's the other way that you can handle this. Yes. Right. So there's your pointer to a pointer, right? So the parameter type is pointer to pointer, is a pointer to int, right? A is a pointer to int, right? So how do I get a pointer to A? I can take the address of A. Right? It's just like before when we did this, right? So here, when I call add one, right, I don't pass in Y, the value, the variable that I want to change, I pass in the address of Y. Any other questions? So there's pointer to a pointer, right? You might very occasionally see a pointer to a pointer to a pointer. They're doing work construction outside. So very occasionally, so if you work with a two-dimensional array, you might see a function that takes in a pointer to a pointer to a pointer. And the general advice is that you never expose users to pointers to pointers to pointers. So you try to rewrite your function in a way that you don't have to, that the caller doesn't have to deal with pointer to pointer to pointer. Right? Generally, that's the most complicated thing that you want to force your users to have to deal with. All right, so on the assignment that just came out last night, there is a question that forces you to deal with one of these. So I'm just going to show you the assignment question if you haven't seen it. Where's that? There we go. All right, so question 4 on the assignment asks you to write a function called string self_cat. So this function here is supposed to take a string and concatenate the string onto itself. Right, so if you have the string hello, it should change the string so that it becomes hello, hello. Right, so the only way for this function to work is that for number one, string's just an array, right? So if you want to concatenate something to the end of the array, you have to make sure there's enough memory in the array to hold the concatenated result. Right? There's no way for this function to know ahead of time that there's enough room in this array to hold the concatenated result. Right, so what does it need to do? It needs to allocate a new array, right, to hold twice the length of whatever S is pointing at, right? And so once you allocate that array, you can then copy S into that array twice, right? And then set S to put, or dereference S, and now set it to your newly allocated array. Right? So here you're going to, the caller is going to pass you in a pointer to a string, right? And you're going to adjust that pointer so that it points to a newly allocated chunk of memory that holds the concatenated string. Right, and so here is the caller's original string or original array that's going to hold the string. So it's going to hold the alphabet here. Right, when they call the function, right, they're going to pass in an address. They're going to pass in the address of str. Right, the function is then going to make str point at a different, possibly point at a new chunk of memory. All right, but sorry, go away. Oh, this is so I had to record using Teams, and so that's what you're seeing at the top there. All right, so if you're still confused, and you probably are still confused about this pointer to pointer syntax, right, the notebook walks you through exactly what's happening step by step. Right. All right, so all of the memory allocation, so malloc returns null, or the standard says malloc returns null if malloc can't obtain enough memory to satisfy the request. Right, so in principle, malloc and the other memory allocation functions, they can fail. Right? If they fail, a null pointer is returned. So if you look online for what should I do or how should I use malloc or the other memory allocation functions? They'll say, well, you call malloc like that, right? And then immediately after calling malloc, you check to make sure the pointer that's returned is not null, right? So here, if not string, right? If that's true, then you know that the pointer returned is null, right? And you should do something about it, right? And so if you stop and think about it for a second, right? Why did malloc fail? Well, it failed to get enough memory. And so what should I do if I couldn't allocate some memory for this task, right? And so if you look for answers on that question, basically the summary of the advice is, well, it depends, which isn't very useful, right? So here's the basic line of thought, right? Your memory allocation, malloc has failed, right? So it could not return a pointer to a newly allocated chunk of memory. So what does that mean? It means your operating system couldn't satisfy the memory request. Well, what does that mean? It means your operating system is basically out of memory. Okay? What can your program do if the operating system is more or less out of memory, right? So there's probably nothing your program can do if the operating system is out of memory, right? So there's no sensible thing that you can do to recover from this error, right? I guess you could wait. Hopefully more memory shows up eventually, right, somehow. But in general, there's nothing really you can do. So one of the things you could consider doing is like, well, is to give up, right? I can't get any memory. I can't make any progress in this program. I'm just going to shut the program down and it's up to the user to deal with this consequences, right? So you might consider, well, shutting down the program. So to shut down a program cleanly in C, you can use the function exit. Right? So exit, you pass in an exit code, causes in C, causes any open file streams to be shut down, flushed and closed, right? And it terminates the program, releasing whatever memory is used by the program back to the operating system. Right? And so often you'll see something that looks like this. Right? So if malloc fails, right, you're going to print an error message. To print an error message, I might have told you how to do that on the previous assignment. You can use this function called fprintf. We'll look at this function in more detail later on. Right? If you write to the standard error stream, this message will show up on standard error. Right? And then you can exit using some standard exit code. So here, exit failure is a constant defined by the C library that sets some standard exit code. I don't actually remember what the value is. It's some compiler-defined exit status value. You can pick a different value here if you want. Right? So in a Linux environment, that thing there is the exit status of your program, of your process. All right, so you might have a more sophisticated program. So you're probably never going to see this in undergrad. Many programs try to manage their own memory. So you'll have a program that's probably long running that will try to allocate a big chunk of memory ahead of time, and then it's going to it'll manage its own block of memory. So if you're in that sort of situation, right, your program already has a big chunk of memory allocated, you need some more, right? You might be in the position where you can release some of the previously allocated memory that you had before. Right? So it might be possible in some circumstances that your program doesn't have to exit, but it instead can do something else. So you might be in that situation. Again, probably never going to see that situation in undergrad. All right, so what happens in real life? So there's this big blue box here that talks about what actually happens. So the standard advice is you should always check for null after calling malloc. Right? The problem with this advice is that the only commonly used desktop environment or desktop operating system that actually returns null from malloc is Windows. Right? Mac doesn't do it, Linux doesn't do it, Unix doesn't do it, right? None of the other major operating systems return null from malloc. In other words, malloc never returns null. Right? So if you're in a situation where the operating system is in a low memory condition, right? All those other operating systems have what's called where'd it go? They have a separate process that starts to kill off other programs to get back memory for the operating system to use. So we click on that link there. that will take you to a research article here. And you can see its title there. So it's called When Malloc Never Returns Null Reliability as an Illusion. Right. So if you're interested in this sort of stuff, you can take a look at this paper where the authors of the paper describe the experiments that they ran to see, they actually tried to see which operating systems actually return null when you try to allocate memory that the operating system doesn't have. Right? And they find out that only Windows is the only one that actually does return null. Right? Where to go? Oh, here it is. So all your other operating systems have what's called an out-of-memory, a system component called an out-of-memory killer. Right? And so what starts to happen when you start to run out of memory is this out-of-memory killer starts to kill off processes that are running to try to get back memory for the operating system to use. Right? Otherwise, malloc never returns null. So in practice, on many operating systems, testing for null does nothing. And they argue that where to go here, and they argue that testing for null only creates the illusion of reliability and is wasteful. Okay, so for the purposes of this course, I think in most of the code that I show you, I do test for null from malloc, but I don't actually require you to do it yourself. So unless you're asked specifically otherwise, you don't have to bother testing for null in this course. For when you're using malloc or the other memory allocation functions. All right, so are there other memory allocation functions? Yes, there's two. calloc is similar to malloc, except for the way you call it, slightly different. The major difference between calloc and malloc is that calloc sets the return, zeroes out all of the return to memory before returning a pointer to the memory. So the way you call calloc is you instead of passing in the total number of bytes of memory that you would like, right? You ask for enough memory to hold that many objects of that size. Right? So it's slightly different the way you call it. So like malloc, calloc in principle returns null if it fails. Right? Here's an example. Here are several examples of using calloc. Right? So remember, 1, that's the number of objects that you want. Right? The next number is how big is each object. Right? So calloc 1 means allocate enough memory for 1 car. Right? So C now points at 1 car worth of memory. So if I dereference C, I can set it to some character. I'm going to set it to A. If I want 1 int, right? Size is 1. Num is 1. Size becomes size of int. Right? So I points at 1 int with the memory. Right? Dereference I can now set the whatever value I like. I have an array of int. So here's the function that allocates an array of int. Right? This time it's an unsigned array of int. Right? It's going to allocate an array of unsigned int, length unsigned ints. Right? So to call calloc, it's just length, right? The number of unsigned ints that you would like, times how big each unsigned, comma, the size of each unsigned int. Right? If you have a structure, it's just the size of your structure. Right? So back here, we use calloc to allocate enough room for 1.2 structure. Otherwise, there's no difference between calloc and malloc, right? So calloc is handy if you're allocating memory for strings, right? Because it writes zeros into the returned memory, right? And so that means you never have to write in the null terminator yourself at the end of if you're using that chunk of memory for a string, right? You're guaranteed that no matter what characters you write into the array, after the last character there will be a 0, right? So that satisfies the requirement that all strings be null terminated. Okay. You might ask, well, shouldn't I always use calloc? And the answer is, so in practice, it doesn't really matter, at least on a desktop operating system, right? You can either use calloc or malloc. There's a question of whether or not calloc has to do extra work to zero out the memory. And the answer to that question is it's very complicated. Right. So modern operating systems and their memory allocators are very sophisticated software components. There's no easy answer to whether or not calloc is faster or slower than malloc. All right. So realloc is the third allocation function that we want to look at in this course. So it's fairly common that if you're doing dynamic memory allocation, you allocate memory for something, and then you realize later on that either you've allocated too much memory or you need more, right? And so realloc is the function that reallocates a block of memory. So reallocates a previously allocated block of memory. That's the important part here, right? So you can only use realloc if you've already used malloc or calloc to allocate a chunk of memory. So the way it works is it's called realloc. Right? PTR is a pointer to a chunk of memory that was previously allocated by malloc or calloc. Right? It must have been previously allocated. It could also have been previously allocated by realloc. So PTR must point at memory that was previously dynamically allocated. New size is the number of bytes that you would like your new chunk of memory to have. If that thing is null, then realloc behaves like calling malloc, right? So it will allocate a new chunk of memory for you. That thing there is not supposed to be 0, right? So the standard says if it's 0, you cannot use the returned pointer for anything. So don't try to allocate a block of memory that's 0 bytes long in C, or generally avoid it. Okay, so this thing here returns a pointer, which you're going to need, right? So you're probably going to need to reassign your previous pointer, this one here, right, to the return value of realloc. So the pointer that's returned by realloc is a pointer to the chunk of memory that has that size. Right. Now realloc does some other stuff too. So that's a previously allocated block of memory, right? If you're reallocating that block of memory, you've probably already put something in that block of memory. Right. So for example, if that's a pointer to the first element of an array, you've probably populated the array with some values that are important to you. And so what realloc does is it makes sure to copy anything that was in your previous chunk of memory into the new chunk of memory. Right. So you don't lose what you don't lose the values in the memory that you previously had. You're not allowed to use this pointer. Whoa, sorry. You cannot safely use that pointer after calling realloc, because realloc may have moved the contents of memory somewhere else. All right. Okay, so if you reallocate a block of memory that's bigger, so PTR points at say 8 bytes and new size is 100 bytes, right? Then the chunk of memory that you get back has the 8 bytes that you originally had, right? And then everything else is just some random values, right? So it's uninitialized memory. So conceptually, what realloc does is the following. Right? So it allocates a new block of memory of new size bytes. Right? So you can think of it as going out and asking the operating system for some more memory of sufficient size. Right? And then it copies whatever it was here into your newly allocated block of memory. Right? And then it frees the previously allocated block of memory. Right? So that's why you should you're no longer able to use your original pointer. Right? And then it returns a pointer to the newly allocated block of memory. Right? Now, what it actually does is way more complicated, right? And it depends on your operating system and the actual implementation of realloc that you're using. Right? So for example, on many operating systems, well, in Linux anyway, if you allocated a small block of memory and then call realloc with a relatively small block of memory, realloc probably doesn't move anything around, right? So it probably just expands the block that you had previously, so that you can now hold that many bytes, right? So this allocate a new block of memory does not necessarily happen, right? Similarly, you might be able to shrink a block of previously allocated memory without having to copy or move anything. So here's an example of using realloc to expand the capacity of a string. So first thing I'm going to do is I'm going to make an array of length 5, right, using malloc. Right, so I can hold 5 cars, right, which means I can write a string of length 4 into that string. So I'm going to use string copy to copy the string sysc into my newly allocated chunk of memory. Right, and if I print that out, that'll work just fine. Right, string copy writes the null terminator onto the end of the string for me. Right, I'm writing 4 characters plus 1 null terminator, so that will fit into a block of 5 bytes. So this should work just fine. Right, and it seems to work fine anyway, right there. Okay, so now I'm going to try to make a longer string. So I'd like to write sysc, I don't know, 220 or something into this string. Right? So I need more memory, right? I only have 5 bytes, and I need 8, right? 7 for sysc 220, plus 1 for the null terminator. So I'm going to reallocate the string that I previously allocated. So I now have 8 bytes of memory, right? Realloc returns a pointer, so I need to keep that pointer somewhere. Right, so I need to remember what that pointer is going to be. Here I'm testing for null, right, in the standard way. Right? And now temp, right, now holds whatever str had in it from before. Right, so I can now safely print out temp because I know that str had sysc followed by the null terminator. Right? So I can safely print out temp here, and that works just fine. Right? So temp is now sysc. Right? Now, typically, what you do, right? So typically in these, you want to use your original variable here. Right? So typically what you do is you end up reassigning the value from realloc back to your original pointer. Right? So that's not unusual to see. Right? So reassign the result of realloc back to your original pointer str. Right? And now I have a str points at a block of memory that's 8 bytes big. So I can now use string cat to concatenate 220 onto the end of str. Right? And when I print that, that should be sorry, am I using, no, that should be str, sorry. Copy and paste. Oh, it's printing out the wrong thing too. It doesn't actually matter here. Temp and str both point at the same thing, right? And so it now prints out the string sys220, which is the correct and desired result. Also, don't forget when you're using these allocation functions, you should always free the memory when you're done with it. In this course, a lot of the time you're doing the reallocation in a main function, right? When main ends, your program ends and all the memory gets returned back to the operating system anyway. So here in practice, you don't actually need this particular free here, right? The memory is going to get freed back anyway. Okay, so the free function is the function that returns a previously allocated chunk of memory back to the operating system, right? So whatever pointer you get back from malloc or calloc or realloc, right? Eventually, you have to remember that you got to free that pointer, right? Or sorry, free the memory that the pointer points at. If pointer is null, free does nothing. Right? If pointer points at a chunk of memory that malloc, calloc, or realloc previously returned, it will release that memory back to the operating system. Right? So if you try to use that pointer to to access that memory again, you're going to run into problems. Right? That pointer is no longer valid. If PTR is a pointer that came from somewhere else, right? So imagine you take the address of something, right? Then calling free results in undefined behavior. Right? Your program will probably crash. So you have to make, so remember, before you free a pointer, you have to remember that you can only free pointers that were previously, that point to dynamically allocated memory. And you cannot call free on a pointer twice in a row, right? So if you free a pointer and then immediately free it again, that's called the double free bug. You're not allowed to do that either. Some authorities. So this is a secure, this website here is advice for people who are concerned about security in programming. They recommend that you do the following, right? So you allocate some memory, you then use that memory for something, right? So your program chugs along, does a whole bunch of stuff, right? And then eventually you're done with it. So you say, well, I have to free my memory, right? They recommend immediately setting the pointer to null, right? Rather than, sorry, they recommend immediately setting the pointer p to null, right? That way, if someone else tries to use the pointer after this point, right, they're going to be using a null pointer, and the program will probably crash at that point. So remember here that freeing p doesn't actually change the value that p is pointing at, doesn't change the value of p, right? It can't. So after calling free, p still has a value in it, right? The memory that it's pointing at, or the memory that p is addressing, is no longer valid. So that's the reason for that device that's given there. All right, so that is dynamic memory allocation. So you are now in a position to do to complete assignment 5. Right. So assignment 5 basically has you complete a bunch of simple string exercises that all rely, not all, many of which rely on allocating memory. All right, any questions about dynamic memory allocation? Yes. Yeah. So if you just wrote p equals null, right, that says your pointer now points at nothing. But the memory that p previously pointed at never gets returned to the operating system. Okay. So remember here, that call there, right, is your program is asking for some memory, right? So you ask the operating system for some memory, right? Memory system hands you back a chunk of memory, right? If you don't free that memory, the operating system never gets that chunk of memory back until your program ends, right? And so if your program constantly, many programs repeatedly ask for memory, right? Because they're doing a lot of dynamic memory allocation. So if you forget to return these allocated, the allocated memory back to the operating system, eventually the operating system runs out of memory.
Just zeros out the memory really for that to like say this knowledge zeros out the memory.
No. If you just say p equals null, that zeros the pointer, right? So the pointer now points at nothing, but the memory that it was pointed at is still there, right? And is still being used by your program. Yeah. No, the only way to do it is if you happen to have another pointer that points at that memory. And if you don't, there's no way to do it. Yeah. All right, any other questions? Okay, so there's only one other new thing in the course. And so that's reading from files, reading and writing to files. And so the rest of the course is basically putting all the components together to write some system level utilities, more or less. So what is the next notebook anyway? Oh, okay. So the next notebook describes how you make a proper string type in C. So I guess the next few exercises we're going to go through are basically implement simple data structures using C, right? And in our implementation, we're basically we're going to be using a lot of dynamic memory allocation. All right, so C doesn't have a proper string type, right? It just uses arrays of car, and you have to remember to stick in the null terminator to end your strings. If you wanted a proper string type, it's not terribly difficult to make one. There's many different ways in which you could create a string type. The way I'm going to show you in the notebook is the quote unquote obvious way to do it, right? So it would be the way that I think many of you would be able to do this own right away. There are more sophisticated ways to do this. Yeah, so I'm going to show you the straightforward way of implementing a string. Right? So the string that we're going to implement is a mutable string, right? So it's different than Python and Java, where strings are immutable. You know that in C, to find for a plain C style string, if you want the length of the string, that's an ON operation, because you have to search for the null terminator in the array. Right, so we're going to try to avoid that problem there. And we're going to make a string type that is compatible with standard strings. So that if you want to, you can use the standard library functions with our new string type as well. So that's nice. Yeah, so if you search online for a string data type, you'll find many different open source implementations. Yeah, the one I'm going to show you is the quote unquote obvious one. Right. So if you want to make a type in C, basically you're going to create a struct. Right. So struct is C's mechanism for creating user-defined types. I'm going to create a struct called QString, short for queen string. Right. That's going to be our string type. Okay. So what do I need to implement to represent a string? Right. Well, I want it to be compatible with C-style strings. So I need an array of char to hold the characters, right? Furthermore, I have to make sure the null terminator is in that array, right, to mark the end of the string. I would like to not pay an ON price every time I want the length of the string. And so that means I'm going to record how long the string is, right? How many characters are in the string, right? And that's it. So it's going to be a very simple structure, right? So it's going to have a member called length, right? That's the number of characters in the string. The amount of memory that this thing will occupy will be at least length plus 1, right? Because I need to write the null terminator into my array as well. I also need the array. Right? Now, if you remember back to the struct notebook, right? I told you that a structure is not allowed to have a variable length array in it. Right? Here, I want a variable length array. I want it to be of length plus 1, but I can't do that. And so what I can do instead, though, is I can have a pointer to char. Right. And obviously now we're going to dynamically allocate memory to store the string and to store a pointer to the first character in the string in our pointer to char. Right. And so data is going to be a pointer to the first character of our char array that I can store the string in. Oh, what else do we need to know? So we need one more piece of information, right? So remember length, number of characters in the string. Data is the array in which I can store those characters in, right? Its length, the length of that array will be at least length plus 1, right? But it makes sense to make that, it probably makes sense to make that array bigger than that length there, especially if I want a mutable string, because I probably want to add a concatenate to the end of the string. So the other piece of information I want is how big is that array? Right? And so the third piece of information is the capacity of that array there. Right? And that's all you need to implement a simple string type. Right? If you want to think in terms of class invariance, there's no classes in C, right? But if you want to think in terms of invariance, right, we have to make sure that that capacity is always greater than or equal to length plus 1. Okay, so there's our structure. Believe it or not, you could just use that and go with that, and that's you're done, right? So you can say, well, there's your string type, away you go, right? So let's see how you use it in that form right now. So it is usable. It's really awkward. Right? So there's my structure. Right? And if that's all you're going to give your users are going to have to deal with allocating memory, setting the length, and setting the capacity themselves. Right? So I'm going to, instead of making a plain old structure, I'm going to make a pointer to a structure. There is a reason for doing this, which we'll explain towards the end of the notebook. So rather than just making a struct QString, I'm going to make a pointer to a struct QString. Right? It's no big deal to make the pointer, right? You just allocate a chunk of memory big enough to hold a QString structure. Right? Don't forget when you're using structures, struct is part of the type name. Right? Okay, so I've allocated a structure to hold a string. Right? That is uninitialized, that is uninitialized, and that is uninitialized. Right? So now I have to initialize all those values. So it looks like I'm going to make a QString object that can hold a string of length 7. Capacity is 8. So I can hold a string of length 7 in this structure. So I go ahead and set the capacity to 8. I go ahead and allocate my data array so that I can hold 8 cars. Right. And now I can write into the data array. I can write a string into that data array. Right. So here I use sprintf. You could also use string copy. Right. I'm going to use sprintf. I'm going to write the string sys220 into my data array. Right. Also remember that sprintf, when you write a string, writes the null terminator into the array. That has length 7. So sprintf ends up writing 7 + 1 characters into the array, right, which eats up all my capacity. Don't forget, you have to set the length of the string to 7. You can then write that string out to standard output, right? So instead of printing S, right, you have to remember that S is a structure or a pointer to a structure. So I need to go into the structure and get its data array, but I can treat S data like a plain old C-style string. Right? So any string function that I want to use, right, I can just call by passing in S data. Right? The complicating factor here is that you have to remember you may have to go in and change the length after calling one of your C-style string functions. Right? So that complicates things a bit. Right? Of course, when you're done, you should free all the memory that you allocated. And so this is the first time that we've seen a situation where we have a structure that has a member. So we have a dynamically allocated structure that has a member that has also been dynamically allocated. Right. So remember, you should free any memory that you've dynamically allocated. So when I go to free this string, you have to remember that you can't free the structure first. Right. You have to free its data array first. Right. The reason you have to free the data array first is because I need S. Right? I need my pointer to the structure to get to its data array. Right? If I free S first, right, S is no longer usable as a pointer. Right? So I have to free all the members first. Right? Once I freed all the members, I can free the structure itself. Right? And again, this is in the main function, so if you just skip these, nothing bad would happen anyway, right? Because the next line I just return the function and the program ends. Right? But this program does actually run, right? And you get sys2. So you could, if you were a masochist, just give people this and say, there's your string. Right? You have to deal with setting the capacity, you have to deal with allocating memory, and you have to deal with setting the length of the string every time. Right? So rather than doing that, it makes sense to provide a bunch of functions that take care of all of this stuff for users of your type. Okay, so this little program here shows you how easy it is to misuse our structure. Right. So here, I set the capacity to 8. So it's going to be the exact same thing, right? I'm going to set the capacity to 8. I'm going to write sys220 into the array, right? Instead of dynamically allocating my string, my data array, right? I'm just going to make a an array having automatic storage duration, right? So make a little local array. And then you could, right? So this is perfectly legal C, right? You can say that this pointer data points at buffer. Right. So you could write arrow data equals buffer, and that would be fine too. Right. Address buffer 0 is the same thing as buffer. Right. I can then write into that string, right? Set its length, right? And away you go. And now I'm going to return S, right? So I'm going to return a pointer to my dynamically allocated structure. Right. What's the problem? Right. So inside that structure, there's a pointer. Right. What is that pointer pointing at? Well, it's pointing at a little local array. Right. So when this function is done, does buffer exist? The answer is no. Right. So what is that pointer pointing at? Well, it's pointing at who knows what. Right. It's pointing at invalid memory. Right. And so when you try to use this particular function, right, we end up with a funny bug. Right. So here we end up with what's the double free or corruption. Right. So what's happening here? So first of all, notice that it never actually prints the string. Right. It never prints the it never prints sys220. Oh, actually, it does print sys220. So that part actually works. Right. Which means that the pointer data, right, is still pointing at a chunk of memory that happens to hold the character sys220. Right. Even though in principle that array no longer exists after the function returns. Right? So that actually works. The problem occurs when you go to free that array, right? So when you go to free the pointer data, or sorry, when you go to free whatever data is pointing at, right? That memory was never dynamically allocated in the first place. Right? Data is pointing at that thing there, right? Which was not dynamically allocated. So you're not allowed to free that memory. And so there's a bug. Right? That's okay, right? So you can free the structure, right? But your program never actually makes it there, right? When you try to free whatever data is pointing at, that's when you get this double free or corruption bug, and the program barfs. Okay, so what we want to do is we want to provide a bunch of functions that take care of all of this setting of length, capacity, and fiddling around with the data array. Right? And so what we're going to do is we're going to provide a bunch of functions for the user to use instead of having them manually manipulate the data structure themselves. Right? If you give them the structure, right? So if you give them this, right, they can, if they want to, go in and manually manipulate the structure. Right. So for example, they can go in and set the length to 0 and set the capacity to 0, right? And free the data array and stuff like that themselves if they wanted to. Right. So in C, there are no access modifiers like there are in Java. Right. And so you're basically exposing all the details of the implementation to users this way. All right, so basically, we want to take the similar approach to what you learned in 124, right? When you're using this string, basically you're creating new strings, right? So in Java, you'd call a constructor, right? You want to use your string object, so in Java, you'd call a method, and then eventually you want to get rid of it, right? In Java, you don't care about getting rid of objects, but in C, you do, right? We have to free the memory that's allocated. So we're going to provide a function, destroy, that's able to deal with deallocating the memory belonging to a structure. Right, so I guess we should stop there. And then the next class, we'll look at the details of implementing many of these functions. All right, any questions? All right, see you tomorrow.